Hey friends, welcome back again, and in this video I am going to discuss about a very important reaction. So the reaction which I will discuss today, I don't know whether it is came in previous years of CSIR exam or not, but believe me, it is a very important question, so don't miss the video. Watch the video till the end, and now let's begin. So you can see this aromatic compound, a aromatic hydroxy compound, that is a phenol derivative, is reacted with these two conditions. First, it is reacted with this reagent, and second, it is the resulting molecule is reduced with lithium aluminum hydride. Now, what will be the product? And these four options they can give you. Okay, and you have to predict which will be the correct answer. Now when we look at these two reagents, this one and this one, we have to identify which are the reactive centers. So you can see here this aromatic ring, this hydroxyl group is one of the reactive center. So it can either attack through the benzene ring, that is C alkylation, or O alkylation. And C alkylation means electrophilic aromatic substitution, which is a favored reaction whenever you have a very reactive electrophile. But and also C alkylation means C center, whenever you have a O center and C center. C center is a soft center, so whenever you have soft electrophile, generally C alkylation occurs. But in this case, now you have to identify which are the reactive centers. Now you can see this is a reactive center, this is a electrophilic center, and also this is a electrophilic center. Okay, so you can see here a 1,4 addition can occur. If this hydroxy group attack here, a 1,4 addition can occur. And if you look at the options, you can see there is no option for C alkylation. So one thing is sure from the options is that only O alkylation is occurring here. But if you look at the four options, you will think that the difference between the different products is that in some cases the reaction occurs in this position, that is this 1 2 3, or if you nomenclature, give the nomenclature from here, then 1 2 3 4. So in one case it is 4 position is attacked in 4 position undergoing attack, whereas in the other case this 3 position is undergoing attack. And there is the option C where you can see this. So in the option C, you can see this OH group is attacking this position. So this is shocking, and when you look at the options, you will first remove this option. Option C you will remove, because you can see that if any nucleophile attack here, the negative charge goes here. Okay, so this negative charge cannot be stabilized into this carbonyl group, and that's why you will obviously remove this option C from your choice. Now the interesting factor in this question is that option C is the correct answer. Now how will you explain that? So this compound which is given here, it is not a ordinary lactone. This is a lactone, but it is not an ordinary lactone. You can see there is a hydroxyl group, so it is called alpha hydroxylactone. Okay, and if you carefully look at the structure, you can see this oxygen lone pair can push here and it can open. So now what you will have this acid, and here you will have aldehyde group. So one thing now you can notice is that between this acid carbonyl group and this aldehyde carbonyl group, obviously the aldehyde carbonyl group is much more electrophilic than this acid. So if you consider this structure, you can see any nucleophile will prefer to attack here rather than here. But if you consider this structure, you cannot predict that how the nucleophile is attacking here. So this breaking of this bond, as we get it, this is a spontaneous process, because you can see this is a tetrahedral intermediate type structure. This you can say a tetrahedral intermediate, because two electronegative groups are directly bound and both have oxygen lone pair, so they can push, and that makes this bond unstable to break, and this compound will be generated. Now you can easily predict that. So what is in our hand is now is that we have this compound, these two bromine groups here, and here you have this acid, right? And now you can see this oxygen lone pair can attack here to undergo a 1,4 addition, and that will give you this compound. So you will have methyl oxygen here, and now you can see you have this. So you can see here you have this acid group, and here you have one bromine, here you have another bromine, here you have O minus. Now when this O minus push back, this double bond will go here, and this bromine will go out. So what you will get is something like this methyl group here, this oxygen, and here you have this carboxylic acid group OH, and now here you can see you have this double bond, here you have this bromine, and here you have this aldehyde group, right? So this you will get. After that you can see it can again undergo this cyclization reaction to give you this compound, methyl group here, here oxygen, and here you will have a 5-membered ring where you will have a carbonyl group here oxygen, and this OH, here you will have a bromine. Now this oxygen lone pair can again push, and this OH group will go out. Okay, so this thing is in equilibrium. This OH which is removing it can again attack, but the interesting point here is that in the second step you are using lithium aluminum hydride. So here you will have this structure, and now you are using lithium aluminum hydride. So actually it is not lithium aluminum hydride, it is sodium borohydride. So in this case it is sodium borohydride is used in this case. Okay, so sodium borohydride is used, and you can see now if sodium borohydride is given, what will happen? It will reduce this center, so hydride will attack here. This is more reactive than this, you can see, because positive charge on oxygen is there. So here you will have bromine, and here you will have oxygen. So this will be the correct option, and option C which is given. So option C is the correct answer. And so another possibility is also there. Instead of undergoing cyclization in this step, as you can see, sodium borohydride is given here, and you know sodium borohydride cannot reduce acid, but it can reduce aldehyde. So in this case it will selectively reduce this aldehyde. So after this step you will have alcohol here. So sodium borohydride will reduce, and you will have alcohol. Now this alcohol, you can see this alcohol can undergo cyclization. So this is another option, but either way you will get the same product. And I think this step will be, this is indeed will be the mechanism. I don't know, I don't have the real in the real paper they didn't mention the mechanism of this step, but what is more probable is that this is the correct answer, because this is more logical, that you are using sodium borohydride, so it will selectively reduce this aldehyde instead of this acid. But these two are separate step, and we can indeed trap the intermediate after the first step, so that can tell us what if this reaction is occur in this mode, that is this aldehyde is first reduced or the cyclization is first happened. So either way you will get the same product. So this option C you will get. So this is very important. If you don't know that these can open and exist in the open chain form, you can never predict which will be the correct answer. So this is why I am discussing this problem with you, and I think this will be helpful for you. This question can come in any year of CSIR exam, because they pick questions from papers, and this is one of the step of the natural product synthesis. So this is very probable question, and if you like the video, then share it with your friends, and don't forget to subscribe my channel, and also press the bell icon for notifications. Thank you for watching.